In chapter 7, we talked about samples when we knew information about the population parameters. But in reality, we're not actually going to know or generally know the population parameters. We'll only know a sample that we have collected. So in the next few chapters, we're going to be looking at unknown parameters collected from a sample. And in chapter 8, we're going to attempt to estimate unknown parameters using something called a confidence interval. So the first thing we want to define is something called a point estimate, which is using one number to estimate a parameter, which, as we kind of discussed in chapter 7, is a bad idea because we talked about sampling distributions and we took many samples in order to show that our sample statistic or sample proportion could estimate the parameter. But if we only use one sample to estimate a parameter, we know that this could be really far above, really far below the actual parameter, which is why it's a bad idea. So for example, if we collected data from an SRS of 60 STAT 1350 students about their study habits, and 50 of the 60 say that they studied more than 5 hours a week, what estimation of the population proportion can be made and how good of an estimate is it? So we know that P hat is going to be 50 over 60, which is 0.83, which means that would be our population parameter, which means our proportion would also be 0.83. So it may be good, it may not, but it is subject to variability. So remember, we talked about how we reduced sample variability by having a large sample size. So only collecting one statistic, the 0.83 could be accurate, but it may not. So how we get a better estimate is with an interval. So when we use an interval, we're using, so the interval estimates where the parameter lies. So the interval the parameter lies in. So for example, we could say our parameter would lie in the interval 0.81 to 0.85 if we were doing something relating it to our previous example. So what we're going to use is something called a confidence interval. So what that is, so if intervals are created from different samples, C% of those would contain the parameter. So what we're going to do is we are going to choose a confidence interval, and we're going to choose a percent confident to be that if we create that interval, there's that percent chance that it would contain the parameter for that sample. So with that being said, there is a margin of error. So anytime you are calculating something where you want to be like a C% confident or you want to estimate something, there's something called a margin of error. So it is the error associated with picking a sample from population whose statistic does not match the parameter. So again, this is where variability with confidence intervals is going to come into play, is with our margin of error. Okay. So at this time, how we create our intervals, right now we're going to use our 68, 95, 99.7 rule from a few chapters ago. We'll take a closer look in sections 2 and 3 how to do it differently, but right now we're going to use our 68, 95, 99.7 rule. So our example says that suppose that in an SRS of 2,000 students, 80% in truth did study over 5 hours. What is the mean and standard deviation of the sampling distribution of p hat, and sketch a picture of the distribution. So we are going to go back to chapter 7. So our parameter is going to be 0.80, which means our mean is going to match the parameter, and our standard deviation is the square root of 0.80 times 0.2 over 2,000. Which is going to be 0.009. It makes more sense here to round 3 decimal places than 2, mainly because 0.009 is a more accurate representation than 0.01. And then just to make sure it's normal, we'll check that before we sketch the distribution. So n is 2,000 times p, which is 0.80. 80% of 2,000 is definitely greater than or equal to 10, 1,600. So 2,000 times 0.20, 400, also greater than or equal to 10. So it is normal, which means we can sketch a picture of our distribution. And 0.80 would be in the middle. So now we want to use this to find the 95% confidence interval for the population proportion. So if we remember back to before, 95% is 2 standard deviations away from the mean. So our p hat is 0.80. And so that means a 95% confidence interval is found by taking our p hat, 0.80. Whoops, I don't need that plus in front. Okay. Adding and subtracting our 2 standard deviations away, which becomes 0.80 plus or minus 0.018. So 0.80 minus 0.018 is going to be 0.782, and 0.80 plus 0.018 is going to be 0.818. So what this means, if I want to interpret what my confidence interval is, it doesn't tell us how likely it is that we will produce an interval that captures the population parameter. It doesn't tell us that the chance that it captures. It says we can be 95% confident that our interval contains our parameter. Okay. So when we're finding a confidence interval, what we're basically doing is setting up a sampling distribution based on the statistics we found, and we find a margin of error. Okay, so we are going to take a closer look in sections 2 and 3 how this gets more specific for proportions versus mean. But in general, what we do is we take the statistic, we add or subtract the critical value, which is our standard deviations, then, well, it comes from how confident we are, and our standard deviation. So just to recap, there are conditions when we use a sampling distribution, so we also have to keep those conditions for a confidence interval. We have to have random selection, it has to be normally distributed or an assumption already, and it has to be independent, so a sample that is less than 10% of the population. Let me know if you have any questions.